Let's go way back. When advanced node SoCs were mostly digital and lower data rates ruled the world. You know, the caveman days. Yep, let's go all the way back to 2015. I know, we have come a very long way in 6 short years, right? But now, in our IC designs, we need to contend with SoCs with integrated analog, 100 plus gigabit data rates, and 3D stacked DRAM integrated into our SoC on interposers. And what has all of this advancement done? Made circuit simulation even more important than ever before, and a whole lot more complicated. Hi, I'm Amelia Dalton, host of Chalk Talk. In order to keep our heads above water in all of this icy complexity, we need a unified circuit simulation workflow, a fast sign-off SPICE, and FastSPICE architecture. And guess what? We're talking about exactly this today. My guest is Hani Elhak from Synopsys, and we're delving into the details of the PrimeSim Continuum. We take a closer look at how this unified workflow addresses systematic and scale complexity for your next IC design. And before we get started, don't forget to click that link. There you can find even more information about the PrimeSim Continuum from Synopsys. Hi, Hani. Thank you so much for joining me.
Hi, Amelia. Thank you for inviting me to the Chalk Talk.
Absolutely. Now, we're talking about PrimeSim Continuum today. But, Hani, before we jump into the details, can you walk us through exactly what the PrimeSim Continuum is all about?
Absolutely. PrimeSim Continuum is a unified workflow of best-in-class SPICE and FastSPICE simulators. It includes the fastest GPU-accelerated next-generation SPICE technology, delivering 10x faster performance using CPU and GPU compared to just using the CPU alone. It also includes a next-generation FastSPICE architecture, which is 5 times faster than our leading FastSPICE simulator today, and also with 2 times more capacity.
Okay, so Hani, when it comes to IC design, we have come a very long way in a relatively short amount of time. And an important aspect of IC design today is the inclusion of what is called hyperconvergence, right? Can you talk about that a little bit?
Sure. Let's take a look at an SoC from 2015, say a 16 nanometer SoC. It was mostly digital. It had certain mixed signal components like high-speed I/O and embedded memory, but these were small in size, running at low data rate. Analog functionality was designed in discrete analog ICs on mature nodes outside of this SoC. Now, if we fast forward to 2020, an advanced node SoC now includes the integrated analog. So this is a big increase in the systemic complexity because in the past, we cared about designing them together only at the PCB level. Now, the system includes all these analog functions and all of them designed on the same, say, 3 nanometer advanced node that the SoC is designed on. So they suffer from all the advanced node shortcomings and challenges. The integrated analog mixed signal blocks on the SoC, like the embedded SRAM, for example, now we have embedded SRAM, embedded flash. They are much larger than before, and they're much faster. Also, the I/O is now a lot more complex and running at 100 plus gigabit data rate. And this is a big increase in the scale complexity because the same blocks are now larger, more complex, and running at much higher frequency. So we have a big increase in the systemic complexity by including different types of blocks in the same system. And this is the definition of the hyperconvergence.
Okay, so Hani, where are we today in 2021?
Well, in 2021, there is even more increase in both the systemic and the scale complexity. Take the DRAM, for example. The DRAM is now replaced by a large 3D stack of DRAMs, like in the high bandwidth memory, HBM. And this 3D stack of DRAM is integrated with the SoC over a silicon interposer. So the systemic complexity has increased with this 2.5D or 3D IC component, and the scale complexity has increased because the DRAM has increased enormously in size.
Okay, so Hani, when we're talking about hyperconvergence, we also need to talk about circuit simulation, right? How is hyperconvergence changing the circuit simulation landscape?
Hyperconvergence is redefining circuit simulation. In the past, integrated circuits had a limited scope, and it was possible to use different simulators for different types of design. There were simulators optimized for analog designs, other optimized for high-speed I/O, others optimized for memory. Now, with hyperconvergence, all these components are part of the same system. So there is a need for a converged workflow around a common circuit simulation solution. It's not possible anymore to work with point tool simulators that are integrated together in ad hoc flows. Looking at scale complexity, now the system consists of larger and more complex circuits running at higher frequencies. These circuits are designed in advanced nodes, which means reduced margins, increased parasitics, and so there is a need for faster and high capacity simulators. And of course, there should be no compromise in accuracy because these are accurate transistor level simulations. So we need to find ways to run the simulators faster and achieve higher capacity without compromising the accuracy.
Okay, great. Now, Hani, how exactly are we going to deal with this systemic complexity you mentioned?
So we are introducing PrimeSim Continuum. PrimeSim Continuum is a unified workflow of best-in-class SPICE and FastSPICE engines optimized for different types of transistor level simulation for memory, analog, RF, mixed signal, and custom digital blocks. These engines all share common input, common output, and a common use model to ensure consistency across all different types of designs. It's a complete SPICE solution with time domain and frequency domain simulation, SPICE and FastSPICE technology. It includes all types of analysis, such as periodic noise, transient noise, and it supports mixed signal simulation with VCS, and it includes a unified workflow for reliability analysis, supporting things like circuit checks, electromigration, and IR drop analysis, and aging, self-heating, and advanced variation analysis. So it's a complete SPICE solution addressing all different types of circuits with a unified workflow and a common use model.
Okay, cool. Now, Hani, can we dig into the details of this spice? What does PrimeSim Spice buy me as an engineer?
Very good question. So PrimeSim Spice is our next generation spice technology. We may think of it on three levels. First, it has superior runtime performance with golden accuracy. It runs today 3 times faster than any other circuit simulator in the market. The second important point is that it has scalable performance across CPUs. So the more CPU cores you use, the better performance you get. And this applies to time domain and frequency domain simulation. Then on top of that, we are introducing a new heterogeneous compute acceleration architecture on the CPU and GPU, offering 10x better runtime performance compared to running on the CPU alone. So if we think about it, we are 3x faster than any other simulator, and by using the GPU, we are 10 times faster than that. So today we are running 30 times faster than any other simulator in the market. And I would like to say that this is not just about faster transient or time domain simulation. This is a complete SPICE solution with time domain, frequency domain, noise analysis, everything that is needed for analog or signal integrity or RFIC simulation.
Okay, Hanny. So, what are we really looking at when it comes to runtime performance with PrimeSim Spice?
Well, our customers across the world has run PrimeSim Spice against other simulators, and they have reported the results back to us. What we learned from the early adopters of PrimeSim, that PrimeSim runs on average 2 or 3 times faster than the competition. And as you can see here, I'm not cherry picking results. Sometimes it can be just 30% faster. Sometimes it can be 5 times faster. But on average, it's 2 to 3x faster. But what does running 2 to 3x faster really mean? It means that a 3-day simulation can be reduced to a 1-day simulation. It means that at the same time where you're just waiting for the simulation to finish and get the results, you can run 3 iterations of the design, which is a big boost in productivity. And these are all apple-to-apple comparisons using the same machines, same number of cores, and same designs.
Okay, so we also need to keep in mind scalability across multiple cores, right?
That's right. And the bigger the design, the bigger the need to actually run it on more CPUs. And actually, even back in the years when we introduced FineSim, we had the best scalability across multiple CPUs. And we continue to improve that over the years. And today, with the next generation SPICE technology in PrimeSim SPICE, we can achieve 10x better scaling on 16 cores. And the more cores you use, the better scaling you get. And actually, this can be done on the same machine. Also, these cores can be on multiple machines connected through the network. One key advantage here is that we don't only scale for transient time domain simulation, but we also have very good scaling for RF simulation. We can run RF simulation 5 times faster on 8 cores.
Okay, so here on Chalk Talk, we have been talking about heterogeneous compute acceleration quite a lot lately. And this also comes into play here as well, right, Hanny?
Right. And this is really a very important thing for circuit simulation because if you think about circuit simulation across the years, the designs keep getting more complex. Complex in terms of number of elements that needs to be simulated, the number of parasitics, the number of corners. Designs get complex every year, every day. And in the past, designers were able to get a free ride with better machines. So in addition to the improvement in the SPICE technology that EDA in general introduced, there was always the fact that when you run on a better machine, you will run faster. And CPUs were improving by 1.5x every year. Today, this is not the case. We don't get faster CPUs. We don't even get reasonably priced CPUs with a larger number of cores. So the improvement is 10% per year or less. So just by upgrading to a new machine, you just don't run your more complex simulations faster. On the other hand, the GPUs are improving in compute performance every year. They are improving by about 1.5x per year. And it's said that by 2025, GPUs will be 1000x faster than CPUs. So it really makes sense that we port the simulation technology to the GPU. And simulation consists of 2 main steps that are repeated at every time step of the simulation. And we have developed a new matrix solver on the GPU that benefits from the thousands of cores that are on the GPU to solve the matrix faster. And also, we have ported the device evaluation functions on the GPU. With the large number of cores on the GPU, we can almost evaluate every device on a separate core. And this is very useful, especially in advanced node where devices consist of hundreds or thousands of equations. And we have introduced a GPU-friendly data structure for the transfer of data between the CPU and the GPU, which improves the bandwidth and the latency. And the result is that we can run now 10 times faster on the GPU with the same golden accuracy. As you can see here, we are using better hardware and better mathematics. We are not making any approximation in the circuit. So we are not compromising accuracy by any means while we are getting 10x better performance.
Okay, so what are we looking at in terms of performance in this case?
Yeah, we have early adopters who have ran their very big designs using our technology and the GPUs. They were able to achieve around 10x better performance. As we can see here on the left-hand side, there is this frequency synthesizer design with 108 million elements using 4 GPU cards. We were able to get 7x better runtime than the baseline of 8 CPUs. Adding 4 more GPU cores, we were able to get to 11 and a half times better runtime performance. And if we look at this 6 million element Ethernet SerDes, the baseline was 4 CPUs. Adding 1 GPU card, we were able to improve the simulation performance by 7x. And as you can see here, the bigger the design, the more performance advantage we get. And this is because the GPUs have a sweet spot for large, dense matrices. And the bigger the design, the more parasitics, which means more feedback between the different nodes, we get bigger, denser matrix, which means we can run even faster. And this is counterintuitive to circuit simulation. When the bigger the circuit, the more complex it is, the slower the simulation gets. This is the advantage of using this heterogeneous compute acceleration on the CPU and the GPU.
So, Hani, earlier you mentioned FastSPICE. So, can we take a closer look at the details of FastSPICE as well?
Yes. As you know, Synopsys has always been the leader in FastSPICE. We have FastSPICE technology for more than 20 years. We always had the performance leadership, and we have been collaborating with the top memory and mixed signal customers to keep improving our FastSPICE technology in terms of performance and capacity. And it's really on top of this leadership position that we have built this new FastSPICE architecture. The architecture consists of 3 main components. First, innovative partitioning. As you know, FastSPICE is all about dividing the circuit into smaller blocks, simulating them separately, and synchronizing between them. And we have introduced a new architecture that can give even smaller partitions and better optimization of the propagation of event between those partitions. And most importantly, the partitioning is CPU core independent. So we have better load balancing and better scaling across CPUs. The second key component of this architecture is advanced modeling. We have math-based load models and net-based coupling caps and better RC reduction algorithm to achieve better performance with the same accuracy of our FastSPICE simulators. And the third component here is the GPU. The GPU in the case of FastSPICE is not as generic as it is in the case of SPICE because, as I mentioned earlier, GPUs are better at solving large matrices, and FastSPICE technology divides the circuit into smaller parts. So these smaller parts doesn't benefit a lot from the GPU, but there are certain applications. For example, the power delivery network, which is a huge RC network that connects the power and ground to all the blocks in the design. We can solve this huge network on the GPU at the same time as, for example, simulating the memory array. So we can actually solve problems that was not possible before, simulating a full memory with the power delivery network, running the memory array on the CPU and the PDN on the GPU, achieving 5 times faster runtime. So the result of this architecture is 2 to 5 times better runtime. And more importantly, it's really the improvement in capacity, the ability to handle billions of elements in order to simulate the modern large designs of today.
That makes sense. Now, what kind of runtime specs are we really talking about here, Hanny?
Yeah, if we compare, since we are the leader, right? So let's really compare to ourselves here. So the top memory vendors in the world today have evaluated PrimeSim Pro, our FastSPICE technology, and they have seen between 2x and 5x better performance, as you can see in the results here. And again, when we talk about memories need to be simulated with thousands of vectors, on hundreds of corners. So improving the performance by 2x or 3x significantly improves the productivity.
Okay, so honey, it seems like today's designs are getting bigger and bigger by the day. How does PrimeSim Pro deal with today's larger designs?
Yeah, this is a very good question because simulation is not just about running faster. There are problems today that simulation cannot solve. For example, let's take the problem we talked about earlier about the high bandwidth memory. High bandwidth memory is a stack of memory dies. With our current technology, we're able to simulate the controller and two dies, which is great. But with PrimeSim, we can actually simulate the controller and six dies. This is 3 times more memory dies in the same simulation run. And we can achieve that with the 2x higher capacity. We can simulate today 5 billion elements using PrimeSim Spice. And you may ask, why do we need to simulate such a bigger circuit? Yes, we do need to analyze the interconnection between these memory dies. That's what our customers care about. So they want to simulate the whole thing in one simulation run. And we can only achieve that with PrimeSim today.
Okay, so can we talk about the simulation environment a bit? What all does that include?
Yeah, simulation environments have always been optimized to specific problems, whether it is analog, memory, signal integrity. Today, with this unified workflow, we are introducing a comprehensive design environment called PrimeWave. It's our next generation simulation environment with all what is needed for a complete solution from multiple test benches, corners, sweep, mixed mode simulation, reliability, 3D IC support, all included in one environment, addressing analog, RF, signal and power integrity, and memory simulation. It's a flexible and programmable environment. It can work as a graphical user interface. It can also work from the command line to improve existing scripts used in memory and custom digital verification.
So, honey, what else is in PrimeSim Continuum?
Yeah, Amelia. So PrimeSim Continuum is a unified workflow of best-in-class simulation engines. We talked about PrimeSim Spice and PrimeSim Pro, but PrimeSim Continuum also includes PrimeSim Edge Spice, the golden sign-off reference for foundation IP and signal and power integrity simulation. It's the simulator used by all major foundries for developing their device model and for their sign-off. It also includes PrimeSim XA, which is our leading FastSPICE for mixed signal SoC and embedded SRAM. All these different simulation engines, each optimized for a specific type of designs, but they all work together with a common input, common output, and a common use model through the PrimeWave design environment.
Okay, so how does this fit in within the custom design platform?
So PrimeSim Continuum is tightly integrated with Custom Compiler. It is actually the cornerstone of the custom design platform as it is used for both design and sign-off and verification. It is also integrated with VCS for mixed signal simulation and with Verdi for debugging, planning, and coverage. PrimeSim Continuum is also integrated with PrimeLib for foundation IP characterization.
Okay, so Hani, how have PrimeSim Continuum and PrimeSim Pro been received so far?
Most of our leading customers have evaluated PrimeSim Continuum, and many of them are using it in production already. These early adopters have seen 5x better performance with FastSPICE, as reported, for example, by Samsung Memory here, or and 10x better speed up in SPICE using the heterogeneous compute acceleration with the CPU and the GPU, as reported by NVIDIA and Samsung Foundry. Of course, the most important thing about the Continuum is the ability to run the different simulators for the different applications and to do that in a unified use model. Also, Kioxia was one of the early adopters of PrimeSim Continuum, and they reported that it is an all-in-one solution. They were able to use the best SPICE and the best FastSPICE technology across all simulation disciplines, especially through the PrimeWave design environment.
All right, Henny. Well, this has been a lot to take in today. Can you recap your main points?
Yes, I think there are three takeaways here. First, that PrimeSim Continuum is a unified workflow. It consists of the best-in-class SPICE and FastSPICE technology, all sharing common input, common output, and a common use model. It consists of the world's fastest GPU-accelerated Signoff SPICE, running 10 times faster on the CPU and GPU compared to just running on the CPU alone. And it consists of the next generation FastSPICE architecture, PrimeSim Pro, which is 5 times faster with 2 times more capacity than our leading FastSPICE technology today.
Excellent. Well, Henny, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. It's always a pleasure talking to you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about the PrimeSim Continuum from Synopsys. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.